Some may say, why does the symposium connect to service? Isn't the symposium mainly focused on featured speakers? This is a good question. However, I believe that service does fit with the original intent of the symposium because it fosters the creation and innovation of ideas and the idea of learning together. What better way to learn about problems that face your community than interacting with partners in the community? Also, students will learn together as they will be in groups of students participating in these service projects, which spark discussion about the problems they see that are affecting the broader community. Students might pick a service project which enables them to rethink the way they think about a problem that is not purely based on how the academy views it. Also, this year's symposium theme is about exploring new frontiers, fostering creativity, and building character and creating critical thinking skills. We believe that we can better achieve that goal through encouraging the development of empathy through acts of service. When thinking about this new role of the director of symposium, I wanted to understand the essence of the theme for this year, Out of This World. Obviously, this theme is more than just the exploration of outer space or the cosmos. It suggests the importance of human exploration, ingenuity, and imagination. I wanted to explain the common conceptual strands between the speakers that were invited to join us this year. And, it can be kind of hard because it seems they're very much in different fields. However, when thinking about it, based on my own prior understanding of this, I thought about one word, and that is the sublime. Obviously, this is not a word that we use on a daily basis. This word is often associated with other words like spectacular, grandeur, astonishing, marvelous, or stupendous. Often this word is associated with beauty. While I think to some degree these words capture the meaning of the word, I'm not sure it fully encapsulates the nuances of what it represents. In fact, some philosophers define the aesthetics or the look of sublime in much more nuanced terms. The well-known Scottish philosopher Edmund Burke described the sublime was not beauty, but rather a sort of duality that involved a notion of beauty that invoked delight and fear. For Burke, he wanted to know how the self, or the individual, was transformed when confronted with such a reality. To him, beauty alone was fleeting, something that does not last. The sublime experience changes you. It modifies the way you think about the world and your relationship to it. I agree with Burke in his conception of the sublime. I think we can all relate to an experience that simultaneously is beautiful and scary. Something that transforms the viewer can be both simultaneous glory in its look, but it also can make us uncomfortable or uneasy, or it could destroy the way we view ourselves. This transformation could lead to the realization of the real fragility of life, our identities, our relationship with others, our conception of ourselves, and our relationship with the divine. I think the work of all these speakers unintentionally embodies the idea of the sublime. Dr. Dan Seaton's work examines the nature of the sun and all its beauty. Yet studying the sun closer, maybe not looking directly into the sun is recommended, but we realize its potential to inflict massive violence and the sheer magnitude of its power to affect the entire solar system. And it should astonish us. It has the power to nourish all life on the planet, but it also has the power to destroy. Lewis Ward studies the possibility and excitement of innovative technologies that reveal glorious new digital worlds through augmented and virtual realities and would have been considered miraculous just 10 years ago. While this power could unleash the power of the human mind, it could also exacerbate global alienation and continue to consume our ever-dwindling attention span. Sally Stapleton investigates the promise of a better world through unlimited information and the beauty of it, yet this information can be used to spread falsehoods and lead to real-world tragedies that can in some cases cause death, destruction, and instability. Trent Rash's work in music explores the possibility of beauty embedded within the symphony, yet at the same time, it may modify our understanding of where music should come from, who can produce it, and rethink the very essence of how we think about ourselves. Dr. Christian Schwann his career is built upon the idea of how pictures, shapes, and colors all can influence spiritual lives through modern history. The sheer magnificence of art and how it can transform how we see and commune with the divine can also put in its tension with a modern world that seems to defy our needs for transcendence. Yet Dr. Schwen's force us to alter our perception of whether the modern world is truly incompatible with spirituality. All these speakers provide us with work that embodies the complexity of the human experience of a limited being confronted with the reality of the sublime universe around us. Please enjoy this 2024 Hancock Symposium. Perhaps your experience will not be sublime, but I believe it will be a truly memorable experience that may force you to rethink some common assumptions about yourself, about other humans, and the natural world. Perhaps you will experience something truly out of this world. Next, I'd like to introduce Dr. Laura Stumpy, Associate Professor of Physics. She will introduce our next speaker for our first plenary session.
Good morning and welcome, everyone. It is my pleasure to introduce the plenary speaker, Dr. Dan Seaton. Dr. Seaton is a solar physicist at the Southwest Research Institute in Boulder, Colorado. He is known for his studies of the solar corona. In particular, he produces and interprets images using visible and extreme ultraviolet light. Dr. Seaton received his BA in astrophysics and mathematics at Williams College in 2001, and he earned his PhD in physics from the University of New Hampshire in 2008, where he studied magnetic reconnection and solar flares. From 2008 to 2015, he helped develop and lead the operations and data analysis for a groundbreaking extreme ultraviolet imaging instrument at the Royal Institute of Belgium. His current work includes a study of the sun's middle corona. He leads the Science Operations Center for the Punch mission, a NASA small explorer, and is the project scientist for the Sunset mission. He also leads the imaging and analysis section of the Department of Solar and Heliospheric Physics at the Southwest Research Institute. In true liberal arts fashion, Dr. Seaton is also known for his work in sports journalism, covering cycling events in Europe, such as the Tour de France. Today, he is giving a lecture on living in the atmosphere of a star, how solar activity affects us on Earth, and why you should care. Now, without further ado, please join me in welcoming Dr. Dan Seaton.
Thank you, Laura. Thanks to all of you who are coming to hear about our star. And a special thanks to the IT folks who are currently working desperately to get my presentation on the screen and have been incredibly accommodating. While they're working on getting the slides up, I will tell you that the theme of this symposium is about, I think, looking outwards, into the world beyond ours. But I would like to reframe that discussion a little bit and think about how what's outwards affects us inwardly here on the earth, and how the sun can enhance and disrupt our lives in unexpected ways. So I think we're almost there. Let's see. Are we good? There we go. Okay. I'm going to switch to this wireless.
Is this working? Yeah, okay. That way I can see what I'm talking about, because they're still working on the monitor down there.
So I'm going to tell you about what it's like to live in an atmosphere of a star, which you don't know
That we're doing, but we are.
but I want to...
Oh, I'm good. Beautiful. Okay. Well, I'm still going to use the wireless mic. So I want to ask people if I can, is the clicker? The clicker's not working. It's on. No. Are we good? It's on. Here, I'll give it to you. We'll get there, I promise. There we go. Something happened. So, okay, well, while this image is up there, whether or not the clicker is, there we go. Okay, beautiful. I think you got it. Thank you so much. I got it. Okay, here we go. So what I wanted to ask folks is, maybe it's, oh, you got a different one? This one. There we go. We're really doing it now. Maybe. Why don't you put the next slide on the screen so I can talk about it while we sort this out? So I wanted to ask people, did anybody see the April total eclipse? I see a couple of hands. Oh, a lot of people. And maybe even more people saw it, or at least the people who were here saw the 2017 total solar eclipse. So you know what happens during an eclipse, of course, is that the sky becomes dark because the moon covers the everyday sun, and instead we see part of the sun that is always there and we're always living with, but we don't normally see, which is the sun's corona, the sun's atmosphere. Something happened. Maybe I did that. Okay, something's happening. You got it? Yay! Yeah. Yeah, okay, so the next question is, did anybody see the aurora a month later in May? I got a hand over there. Oh yeah, a lot of people. Awesome. Well, you may not realize this, but if you saw the total eclipse and then you saw the aurora, you're part of a very special club that has seen both cause and effect. The sun, the corona, which is the source of all of the activity that we see in space around Earth, and then the consequence, which is really special. Almost nobody in human history has had the opportunity to witness the cause and the effect in such proximity of space weather, but you guys did, so that's awesome. You were not the only people, however. My field started in 1859 when a British amateur astronomer named Richard Carrington, who'd like to draw pictures of sunspots. He'd look through his telescope. Actually, he'd project his telescope onto, you should never look through a telescope at the sun. He'd project his telescope onto a piece of paper and he'd draw what he saw. And he was doing his ordinary thing, and suddenly he saw this incredible brightening, which he described as bright as the full moon, which I'm not sure what it means because the sun is much brighter than the full moon, but he saw this brightening, these white spots that he drew. It was so bright that he thought something was wrong with his telescope, and he went to find help to get somebody to take a look and see if they could help him, and by the time he got back, it was almost gone, and he was embarrassed. He had missed this extraordinary and weird phenomenon on the sun, which we now know is a solar flare, but he didn't know what it was. And a few days later, there was a huge outbreak of aurora, and for the first time, a disruption of a technical system on Earth by space weather. So there was aurora visible in Cuba and Hawaii and Colombia, all the way down by the equator. And there were telegraph disruptions, right? We had the telegraph by 1859, and the telegraph operators found that they couldn't talk to each other while this was going on. They actually had to disconnect their batteries. And there's this beautiful exchange that's recorded in the record between an operator in Boston and in Portland, Maine, saying, we have to disconnect the batteries in order to get this to work because the electrical currents induced by geomagnetic activity due to this storm were making their telegraphs not work, which is crazy. Well, Carrington was a smart guy, and he wrote a paper about this whole thing, and at the end, he had given a presentation, there had been some discussion, and there's this little note appended to his paper where he noticed that something happened, some connection between what he saw on the sun and what took place. But he was a little, he's ever the scientist, he was a little hesitant to just ascribe causality without knowing the underlying physical reasons. And so he said, well, one swallow does not a summer make. I can't draw this connection. And people thought about this for 100 years, almost, 99 years, until this guy came along, Gene Parker. Gene Parker is really the father of modern solar physics. And what Gene Parker realized is connecting a whole bunch of dots, what the corona looks like, evidence that comet tails always point away from the sun, some new evidence that I'll talk about in a little bit about the fact that the corona is very, very hot, all meant that there had to be some flow of material away from the corona and out into space. And he published this paper, and this slide is not quite right, but it's okay. The details aren't very important. He published this paper where he showed that if the corona is a certain temperature, so say 1.5 million degrees, there would have to be flow away from the sun going, this is a fast speed, 400 kilometers a second. And he realized that that was the solar wind. And this is a really great and wonderful story that I don't have time to tell you, but he proved that even though the sun and the earth are separated by 150 million kilometers, they are part of a connected system, and we are actually living inside the atmosphere of a star. The corona, the sun's atmosphere, is flowing away from the corona out into space and completely enveloping the earth. So that's the beginning. That's the beginning of everything that the people who I work with do. 1859, and then 1958, and then today. Okay, so I've thrown a lot of information at you, but let's actually talk about what the sun is and what it is we're studying. This is the sun, right? Cool. Okay, we're done. This is probably more or less what your experience of the sun is like, right? You look up in the sky and you see a relatively featureless, plain, yellowish ball. We can, of course, zoom in and look in visible light and see sunspots here and here. And sunspots in them of themselves also don't look that exciting, but we can zoom in on the sunspots and see that they're actually really complicated and moving and roiling and boiling. You can see that they have a dark umbra, they have these really complicated penumbra, and then you can see all the boiling sort of convective motions of the sun outside them. Sunspots are places where the sun's magnetic field, which is very complicated, pokes through the surface of the sun in a concentrated way, and it causes the plasma, the super hot ionized gas that the sun is made of, to become a little bit cooler, and so it looks a little darker. And we can see them with telescopes, we can look at the details, but there's a lot hidden. If we dig a little deeper, we can actually measure the sun's magnetic field that's associated with sunspots. And that's what you see here. There's these regions of white and black are actually showing, through a complicated measurement, where the sun's magnetic field is and where it's pointing out and where it's pointing in and where it's strong and where it's weak. And you can see that it's quite complex. There's a lot of mixing of black and white. That means that something interesting might happen on the sun. And if we keep going, and hopefully this will play, we can go back, we can look at these things, but we can start to look at other wavelengths of light that show us stuff we cannot see with our eyes. We can look in ultraviolet light. This is extreme ultraviolet light. You can see the wavelength up here, and each image shows stuff at a different temperature. And you see the temperatures are really, really high. So as we look, you see, 1 million degrees, a couple million degrees. The corona is really, really hot, and this is one of the great mysteries of my field, that the corona is so hot. The surface of the sun is only 6,000 degrees, and you can imagine if I put a 6,000 degree object here in the middle of the stage, first of all, it would start a fire, but if it didn't, if you stood close to it, you'd be very, very hot, and as you walked away, it would get cooler and cooler and cooler. But that's not what happens in the solar corona. The further away you go from the sun, the hotter it gets, and this violates the laws of thermodynamics as we know them, and so some process has to transport energy out from the inside of the sun into the corona to heat it up, and it turns out it's the sun's magnetic field that does that, although we still don't know how that happens. And it turns out that this magnetic field, in addition to heating the corona, can store a lot of energy, and it can make all sorts of interesting things happen on the sun. It can lead to all of these beautiful, complex structures. You see all these loops, all of these bright features, all of these dark features. Those are all tracing out the sun's magnetic field. Million-degree plasma, super ionized gas, filling the loops of magnetic field. And you may have done the experiment with when you were a kid with a bar magnet where you put iron filings and you can kind of trace out the magnetic field. It's the same thing, but with million-degree plasma instead of iron filings. And actually, because the sun's surface is moving around, that wiggles the magnetic field, and it leads to all of these cool motions and brightenings and interactions that happen in the corona that drive the sun's activity. And you can kind of see here, this region here that we call an active region is just full of complicated little motions. But it doesn't do that the same way all the time. In addition to all this, the sun actually also, its magnetic field is evolving over the course of 11 years. Every 11 years, the sun goes through an activity cycle. So we start out with a relatively uncomplicated sun, and the sun's magnetic field is not very complex and not very energetic. And over the course of 11 years, you can see that these images get much more complicated and much more busy, and then back to quiet. And people have known that this cycle is going on for hundreds of years, but again, we don't really understand what drives it, exactly why it happens. But we do know that when you're at a period of maximum activity, like we had in 2013 and 2014 and 2015, the sun becomes active and interesting things happen. And you may note that it's been about 11 years since the last time this happened. So we're at a great time for interesting things to happen on the sun. This is the kind of thing that happens. Huge explosions. The most energetic things that happen in the solar system anywhere. These explosions are so energetic that they release, in a matter of minutes, vastly more than all the energy produced by humanity in the whole history of time. So if you go back to like the origins of humanity thousands of years ago and account for every fire, every campfire, through the industrial age, every locomotive, every power plant, every rocket launch, this energy dwarfs that. And instead of taking 10,000 years to release it, it's released in a matter of minutes. And just to give you a sense of scale, this is the size of the Earth. So these explosions are hugely more expansive than the Earth. They cover vast distances in just a matter of seconds. And this is the Earth to the moon. So you can see this eruption that happens over the course of a couple of minutes, travels the distance of the Earth to the moon in that time. And if you think about how long it took Apollo astronauts to go to the moon, it took them several days, traveling faster than any human being has ever gone. You can get a sense of how energetic these events are. So these events are really cool and they're really beautiful and they tell us a lot about how energy is stored and released in the corona, but they also sometimes happen at the center of the sun. Here's an example, and you can see that there's a big bright thing that we call a solar flare. You can see there's a release of, it'll play again. You can see this dark structure sort of blows apart and releases all this cooler dark plasma. When I say cooler, I mean 50,000 degrees, not cool. And you can also see that there's a big shock wave that travels out. And we can zoom out a little bit and process the data carefully. And you can see that that huge shock wave actually travels out and envelops the whole sun. Travels across the whole sun and disrupts the whole sun's magnetic field, again, over the course of a couple of minutes. And we can zoom out even further, and you can see that that shock wave just keeps going. And you start to think, you know, this is coming straight at us, and it's got a lot of energy, and it's very high temperature. And we can pull back even further, and now I'm not showing you data, I'm showing you an animation, but you can see how this outflow from the sun is coming out and enveloping the Earth. And here's the Earth, and you can see in a second that the Earth, this stuff is sort of floating around the Earth. The Earth is actually protected from this material by our magnetic field. And you can kind of see that here in the movie, the magnetic field lines shielding us from the bulk of this stuff. We can look at this another way. This is actually a computer simulation of what happens to the magnetic field of the Earth when these events travel outwards and interact. Here's the Earth and the moon going around it, and here's the actual computer simulation of the magnetic field. And you can see it's not just static sitting there protecting us, it's interacting with the solar wind, and you can see all these little brightenings, which are actually places where the magnetic field is being reconfigured by the outflow coming from the sun. And if we zoom in even further, what you can see is all of these interactions are taking place in an environment where we have thousands of satellites. Each one of these green points is a satellite going around the Earth in different orbits. The ones farthest out are the ones we use for weather prediction and TV broadcasts, and as we go in closer and closer, there are satellites that do all sorts of things. I mean, literally thousands of them going around the Earth. And you can imagine that these satellites are in an environment where if there's all these complicated magnetic interactions, there are hazards for them. If you could take down a telegraph wire with a solar storm, certainly you could take down a satellite, right? And it's true. So these are some of the things we worry about when these solar storms pass out from the Earth, from the sun and reach the Earth. They can do things like cause the aurora, which is great and exciting and beautiful, but they also have a lot of effects on technological systems. The magnetic currents that come from the interaction, or the electric currents that come from the interaction of our magnetic field and all this material coming from the sun, They can knock down power grids. In 1989, a solar storm took down the power grid of Quebec for a long time because nobody was prepared for the fact that if a solar storm occurred, their power lines would have massive extra amounts of electricity flowing in them, and it blew out all their transformers. These are real hazards for astronauts. Now, astronauts on the space station are in low Earth orbit. They're protected by our magnetic field, but we're going back to the moon. I don't know if you know this, but we are planning to go back to the moon in the next few years. And those people will be fully exposed to all this radiation that comes out from the sun. So we have to protect them. We have to make sure that they know how to shelter themselves. And then it can disrupt communication. It can cause interference with the communications that airplanes use, and also actually expose air crews who travel all the time to radiation. You might think this is not relevant to me, but even in this community, which is in an agricultural center of the United States, this stuff affects agriculture because large-scale farms use GPS to coordinate the movements of their equipment. And if GPS is not working because the radio signals that it uses are being interfered with, you can't go out and harvest your crops. And if you miss that, that can be hugely economically ruinous. It also affects, believe it or not, animals. There's a lot of evidence that whale beachings are sometimes caused by changes in our magnetic field induced by these storms. And oddly enough, it affects racing pigeons. People race pigeons, they take them out and they set them free, and they have to see who flies back to the home base fast enough. And these pigeons cost millions of dollars, so you better believe that the people who race their pigeons, they're calling up every day to the people who forecast space weather and saying, is it safe? Am I going to lose my $1 million bird? And it happens, actually, that these birds, they get lost. They use the Earth's magnetic field to navigate. So space weather is really important to understand. But to understand it, we have to understand the sun. And so what I want to tell you about for the rest of this, I've kind of given you the reason that we care. I want to tell you about how we do it and what we're learning. So how do we observe the corona? And I'm going to do this in a sort of a little bit of a nonlinear order, but what I wanted to do is sort of start off with where we began, where we first started to understand the corona, and then we'll build out to the space age and some of our most cutting-edge technology. So solar eclipses are how we first learned that there was a corona, and people didn't know what it was for a long time, and then eventually we started to figure out what it was. But we started here. Actually, thousands of years ago, people would observe eclipses and make these drawings. They saw something around the sun, they didn't know what it was. And by the 1800s, people started to know that it was part of the sun, or maybe something that was between us and the sun, but we hadn't really been able to record data, so people started to think, well, maybe we could take photographs. And so this is actually the first photograph of a total solar eclipse from 1851. And some people have made whole careers out of this, just studying eclipses, even in the present day. This is Jay Pasakoff. He was my mentor at Williams College. He saw more eclipses than any other human being ever. He went to every eclipse that happened since the 50s, sometimes going up in helicopters to get above clouds to make sure he saw them, and used these as a vehicle to study the corona in ways we can't normally do on the ground. And he was inspired by a guy named Donald Menzel, who was a Harvard professor, who, among other things, liked to make these funny drawings of the sun as little characters. But Donald Menzel was one of the sort of founding figures in solar physics, and he also realized that there was a story being told in solar eclipses that allowed us to engage with the sun in ways we don't normally do, just as you guys, many of you saw, either in 2017 or earlier this spring. So Jay worked for years with Menzel, building equipment to observe the eclipse, and then became a mentor of his own, and he taught me. And this is how I got my start at a solar eclipse in 1999 in Romania. And this is me at our eclipse experiment at the Cotton Bowl in Dallas in April. And you can see Jay was wearing orange shorts, I'm wearing orange shorts. It turns out that clouds are afraid of orange shorts, and so we wear orange shorts to eclipses to ensure that we see the sun. We're not the only people to do this. Thomas Edison did this in 1878. He took an expedition of people to an eclipse in Wyoming. They had all kinds of problems. They got there and they realized they hadn't booked a hotel and they had nowhere to stay and there was mud everywhere and the same problems that we face with eclipses today. They tried to measure the temperature of the corona, but they didn't know the corona was millions of degrees and their equipment did not succeed. It was not set up for something that hot. In the 20s, people flew this Zeppelin. It turns out the Navy had some Zeppelins that were purchased from Germany, and they flew a Zeppelin up to see the eclipse. They thought, well, if we could get above the atmosphere, maybe we can see some things you can't see from the ground. And this is the crew that did it. It was the dead of winter on Long Island. It was very, very cold. They're bundled up. They're going to go up to high altitude. And they set up their equipment, and there's some great accounts. Navy Captain Littell, who was part of the Naval Mathematical Service, wrote this beautiful account of their trip to the eclipse, and he talks a lot about how they would eat ice-cold bananas and hot coffee while they were up there waiting for the eclipse to happen. They made this movie of the eclipse. This is their movie, and they had a problem that is familiar to me. The Zeppelin is up there in the air, and it's bouncing around, and they could not get a steady image of the sun, but nonetheless, this is, to my knowledge, the first video, analog video, of a total solar eclipse. Now, along the way, some people figured out that if you set up equipment that breaks up the sun's light in colors, a spectrometer, you can actually see different specific lines. And this is called a flash spectrum, and people take these during eclipses, and you can see there's different sort of bright lines. And if you think back to high school chemistry, you might remember doing an experiment where you either used lamps, or you put a little chemical compound in a Bunsen burner and you saw it changed colors. This is the same principle. Different elements at different temperatures emit certain colors of light. And so people did this, and this is how they discovered helium. And they also discovered that there was this one green, you can kind of see it there, line that they couldn't understand, and everybody got very excited. We discovered a new element. They saw it in the corona, so they named it coronium. And for years, people tried to figure out what on earth coronium was. We saw it in the sun, but we don't ever see it on Earth. What is it? Well, it turns out it's not a thing at all. They didn't realize that the corona is 2 million degrees. And it's just ordinary iron that glows, but you have to heat it up to 2 million degrees to get it to glow in this color, and people had not figured out that is a thing that you could do. So after a while, the discoverers of coronium had to admit that there's no such thing. But this is how actually we realized that the corona is really, really, really hot. Well, we continue to use eclipses to do stuff that's hard to do from the ground. NASA has these WB-57 research planes, and we fly those planes to see eclipses. Here you can get a view of what the planes look like. These were originally bombers built in sort of the Korean War era, but they've been refitted with these cameras, which you can't see all that well, but this thing in the nose cone here actually has a whole bunch of cameras, and they observe in infrared. And it turns out infrared light doesn't make it to the ground. It doesn't pass through the atmosphere. And so the only way to see what the sun looks like in infrared is to go up high, and the only way to see the corona of the sun in infrared, for technical reasons, is to do it during an eclipse. And so we send these planes up to about 65,000 feet, and we observe, and this is their view. Oh, there it goes. So this is the view of an eclipse in sped up time from this plane, 60,000 feet above the ground. You can see how the ground gets darkened by the shadow of the moon, and you can see the experience that the pilots have, and the equipment operators just must be incredible. That's their view of the eclipse. Nobody has to worry about clouds up there, so they're very lucky. And they take images that look like this, and this might not look like much, but these are the first images of the corona in infrared light. Very few people in the world have seen these, actually. So this is really exciting. This is one of the first times we've ever shown this. And again, it may not look like much, but it turns out that by comparing the differences in, say, this feature across the images, this is visible, and these are progressively longer wavelengths of infrared, we can actually uncover the processes that make them visible. And that tells us about the underlying physics. And so for the first time, in 2017 and then again in 2024, we flew these planes and were able to make these measurements. So that's following in the tradition of the airborne observatories, but of course you can also do things from the ground, but the problem is that the eclipse shadow moves very fast and you only get a couple of minutes of data. So you can solve this problem, and we did, my colleagues and I, by setting up 35 telescopes all along the eclipse path so that the moon will go from Texas all the way up to Maine successively over each one, and we actually are able to make a continuous movie of the eclipse. But if you're going to set up 35 stations, you've got to recruit a lot of people to do it, and so we recruited amateur astronomers, and they went out in the snow in Maine, they went in warm climates in Texas. We had school groups, we had colleges, we had astronomy clubs, and they all went out and made their observations, and we went to the Cotton Bowl. I already showed you this, and this was our team. These are actually my children operating the equipment. This is my son and my daughter. This is my colleague Amir Caspi, who organized this whole enterprise and shipped 35 telescopes and 35 cameras and all over the country. We ran a small shipping warehouse for a couple of months before the eclipse. And these are the images we got. And what's really cool about these images is that they look cool. But no, what's really cool is that the color is actually telling us about the polarization of the light. So we're able to learn about how light that comes from different parts of the corona is differently polarized. And you may not know that you know what polarized light is, but if you wear polarized sunglasses, you've experienced this. Light is actually an electromagnetic wave, and all waves have a direction of oscillation. And if you use a polarizer, you can cut out all directions but one, this one. And it turns out that reflected light is highly polarized. And so, like, if you wear your polarized glasses, the reason you do this is it cuts out the glare from light reflecting off the road surface. You can do this with a pond. Fishermen sometimes use this, or a river. If you don't wear polarized glasses, you see all this reflection. But if you do, you see right through, because you can cut out all the light that's reflected and just see the light that's coming from below. And we use the same technique with the sun. And we can see the polarization, because what most of the light we're seeing here is actually reflected off of electrons in the sun's corona, which is a whole wild concept to think about, but it's true. And you can actually measure how it's polarized, how much it's polarized, and that tells you about the 3D information. And if you have a whole bunch of telescopes, 35 stations, all along the eclipse track, you can also see how things change from one site to another. And these are just a few snapshots. We haven't processed all this data yet. It's terabytes of data. But you can see each image looks a little different, and that's encoding something about how the corona changed over time. And so for the first time, we can actually measure the changing polarization of the sun's corona over the course of a whole eclipse, thanks to this experiment. So eclipses are cool. You can study the corona in a way that we ordinarily can't, but it turns out that people want to study the corona at times when there's not an eclipse. And the first people who did this realized that you can make your own. So with a device called a coronagraph, you can put a little artificial eclipse. This is a little disk out here, and this is a telescope, and we're observing the sun here, and block out the sun's light and look at the corona without an eclipse. And to give you an idea of how this works, you can see this is the front of the telescope I just showed you, and you can see that the aperture of the telescope here is totally dark. It's completely in the shadow of our little mini eclipse. And we did an experiment where we built a coronagraph, this one, and we took it up to Loveland Pass in Colorado, which is 12,000 feet up. That gets us above a lot of air that would scatter the light that, from the sun that we would like to get rid of. And we used it during a partial eclipse to turn a partial eclipse into a total eclipse. And this is me standing with our little coronagraph up here, looking at the partial eclipse, trying to make some measurements. It was October, which means it was the dead of winter in Colorado, certainly at 12,000 feet. And this is what the images look like. You can see they're very blurry, and like the people with the blimp, we had a lot of wind, so our whole apparatus is kind of jiggling around. But if you look very carefully, you can see there are some features up here and some radial features over here. That's the corona, seen during a partial eclipse, when the sun is not completely covered up. Now, the reason we wanted to do this whole thing is actually because people have been doing this in Colorado for a long time, and we wanted to kind of commune with our history. There was a coronagraph in a town at 11,500 feet called Climax, Colorado, for about 30 years. And oddly enough, that was started out by this guy, Donald Menzel, who we talked about before. Menzel loved eclipses, and he couldn't get his fill, and so he learned that a French astronomer named Bernard Liot had invented this device called a coronagraph, and he built his own, and he tried to operate it in Harvard, but he found that you couldn't see anything because there was too much air scattering the light all around. But he had been born in Leadville, Colorado, at about 10,000 feet, just below this town of Climax, and he realized if he moved his coronagraph up there, it might actually work. And so he enlisted his grad student, Walter Orr Roberts, to go up and move his entire family to this high-altitude location in Colorado. And they built a house. They lived in the house, and their kids were born in this house. And out the back door was the first American coronagraph where American solar physics started. And they made observations that look like this. And to this day, I think this is still probably the best observation of a solar eruption that we have, at least the largest and most dramatic eruption we've ever seen. And you can see some of the same things that I showed you in those movies from space of the solar flare. You can see all this fine filamentary magnetic field. You can see this big thing lifting off the surface of the sun. And these people discovered that these eruptions happen all the time, and they also helped to uncover the connection between these eruptions and interference with radars during World War II. And so this became a really important site for helping manage the war effort during those years. And they also had some fun. They have these delightful monthly reports that talk about, for instance, no injuries on the sled run this winter. So I think the people who were up there, it had to be kind of hardy and outdoorsy, but yeah, they went sledding and they went skiing and they had a lot of fun up there in the mountains. But eventually they discovered that they were next to a molybdenum mine, and operating scientific equipment right next to a mine is not the best thing. It's very dusty. There's a lot of problems with mine equipment vibrating the ground. They moved this thing to Mauna Loa in Hawaii, where it still stands today, and it makes these really beautiful observations. And this is another solar eruption. You'll see it play again over there, and then the corona measured from Hawaii a couple of years ago. So that's great too, but the problem is you can only observe when the sun's out. So then people said, maybe we should go to space. And they started making, over the course of many years, observations like these. These are very similar to the observations I showed you at the beginning of this presentation, except now what we've done is I convinced the National Oceanic and Atmospheric Administration to take their very, very expensive satellite, which is ordinarily meant to point to the sun, and point it to stuff that's not the sun, and actually explore what's happening not just on the sun, but out here. And you can see that there's all these complicated features. Over here you can see all these eruptions happening, and over here you can see these complicated fan-like things with flows, which we believe are the birth of the solar wind. And in a minute I'll show you the same movie processed a different way, and you'll really believe me that we're seeing the birth of the solar wind. We've gotten really invested in this. We have dozens of observatories up there in space observing the sun because it turns out this is important. It's important because it helps us understand space weather. It's important because it helps us understand other stars. It's important because it helps us actually, a lot of the same magnetic field interactions occur in fusion reactors. And so for the future of fusion power, it's really important to understand the sun because it's our only laboratory where we can create the energies that are going to be equal to what we're going to get when we have nuclear fusion, if anybody ever manages to do that. So we have this whole fleet of big observatories, and then we have CubeSats, which are little tiny shoebox type satellites that are all going up and can make sort of dedicated small scale measurements, but really important ones. We have stuff that's all through the solar system, and I'll show you some of that in a minute. So you can take the observations like I showed you, and you can fit things together. Here's sort of the same view of the sun as I was showing you before. And then out here, you can put it together with coronagraph observations. This is from an instrument called the Large Angle Spectrometric Coronagraph, which is on a satellite that launched in 1995 and is still going, which is a whole miracle in and of itself. But when you fit these together, you can start to see this connectedness, right? From what's happening in the sun, down here to out here, these sort of complicated structures over here. And that's pretty exciting. But it turns out that a lot of the stuff that we're seeing is very, very subtle. And so if then you bring really complicated data processing and you get rid of all the stuff that's staying the same over time and you just look at what's changing, right? So all the stuff that we were seeing before, mostly it's static, right? And there's just these very subtle 1 or 2% variations. And we've gotten rid of everything but the variations. And then you look again, you see just how dynamic and how complicated all of these interactions and flows and behaviors are. And over here, of course, you see these very, very prominent solar eruptions. There's one, here's one, here's one. And you can see how they're born down here and they progress outwardly into the sun's atmosphere and then out into the heliosphere where they can threaten us, cause space weather. But you can also see the much more subtle but very important little tiny jets that are happening over here. And if you watch carefully, and I'll let this play for a minute because I think it's really important to see this. These little jets are the origins of the solar wind. You know, we talked at the beginning of this about Gene Parker and how there should be a solar wind, and we know there's a solar wind, but even after he did all his work, we didn't really understand the process that gives rise to the solar wind and its structure and how it gets accelerated. But these new observations from just a few years ago are the first ones that really show us that it's born out of all of these little tiny interactions in jets that flow out from the very base of the corona and into space, and eventually can flow over the Earth and cause space weather, and they can reshape comets. So that's pretty cool. But we can actually take this even farther. So relatively recently, we added the capability not just to look at the sun. This is the ultraviolet images I've been showing you. Here's coronagraph images. We've sort of remapped these onto a grid in a weird way. But James, you can kind of warp your mind and think about just sort of cutting out one part of the image, right? So we're seeing sort of one side of the sun. This is kind of what I was showing you before with the outflows and the solar eruptions coming from the surface of the sun and then out in here. But now we have images that look not anywhere near the sun, but out into the solar system itself, and they're super sensitive. They make measurements of stuff that's 10 to the 17, so that's like, 100 trillion times fainter than the sun itself. Really faint, stuff that's fainter than the stars, and you have to do all this processing to get rid of the stars. But when you do this right, you can actually see then, here are the origins of things that are happening, flowing out through the corona, and then into the solar system. And you can see here's a coronal mass ejection flowing out, and eventually it's going to come to the Earth. This satellite is not at the Earth or between the Earth and the sun. It's actually off to the side, so it can see the Earth and the sun at the same time and give us a sort of a view and profile. And we also have a couple of satellites that are just between the Earth and the sun. They're about 1 million miles closer to the sun. The sun, right, is about 100 million miles away, so they're close to the Earth, but a little further away than the moon. And they can measure the density and speed of the solar wind, and you actually watch their measurements go up and down as these structures sweep by them near the Earth. And let's watch this eruption come by. This is Venus here, and now this guy's coming to Earth. And you see the density goes way up. And all of these things fit together then to give us this complete picture of what's happening, what's coming from the sun, how it reaches the Earth environment, and then what happens in the environment near Earth where all these space weather effects that I was talking about at the beginning of the presentation occur. So that's real progress, but actually we've taken things even farther in the last couple of years. One of the things we've done is the European Space Agency has launched a mission called Solar Orbiter. And Solar Orbiter does two things that are cool. The first is that it gets much closer to the sun than we've gone almost. I'll tell you about the almost in a minute. But it also is leaving the plane. All the planets actually orbit the sun in the same plane, right? If you looked at the solar system from the side, what you'd see is the sun and then all of the planets stretched out like that on the sides of the sun. And we have never really left that plane. It turns out it's really, really hard to do. It takes a ton of energy and a really big rocket. But for the first time, we launched this satellite that actually, using a bunch of passages around Venus and using Venus's gravity, was able to get out and show us, believe it or not, we have no idea what the sun's north or south pole looks like. We've never seen them. But for the first time, sort of at the end of this mission, 2029, 2030, we're going to get a glimpse, our first glimpse of the sun's poles. And that's really important because, just like the Earth, you may know that the Earth's magnetic field largely originates from the polar regions. It's also true with the sun, and we have no measurements up there. So that's going to be really exciting. But I can't show it to you yet because I'd need a time machine. What I can show you is some of the closest views of the sun. And so these are the same regions I've been showing you, but now super zoomed in, taken from inside the orbit of Mercury. These are the highest resolution images of the sun, of the corona, I should say, ever made. And you can see how all these structures I've been showing you, all these magnetic loops, they're actually really, really complicated. These just beautiful filamentary structures, all of these twisted features, all of these interacting flows, all of these brightenings, these are extraordinary. These are, for the first time, revealing, not just sort of the superficial level of what's happening in these regions, but all of the complexity that actually is what gives rise to activity, solar flares, and all that stuff in the first place. So that's kind of the cutting edge, but actually we've gone even farther. You remember Gene Parker we actually named this satellite in honor of him, the Parker Solar Probe. And this thing has gone down almost to touch the sun. It is actually literally flying through the solar corona, the million-degree solar corona that I showed you. And obviously, to do this, it has to have incredible heat shields and be really amazingly engineered. But you can see it has this really weird orbit where it kind of goes out from the Earth, and then it sweeps by the sun right here, and then back out, kind of like a comet. And it turns out that it's really hard to send things to the sun. You have to get them going really, really, really fast. It's much harder to send things to the sun than it is to send them out of the solar system, in fact. We sent things out of the solar system in the 70s, the Voyager spacecraft. But to send stuff into the sun, that close to the sun, is really hard, and we needed really big rockets that could do this. And this satellite, when it goes by the sun, it's traveling at 430,000 kilometers per hour. I flew here from Denver yesterday, a 2-hour flight. That flight would take 11 seconds at that speed. So really fast. This is the fastest thing that humanity has ever built. And it literally flies through the solar corona. So this is, again, a kind of complicated image to wrap your head around. We're seeing 1 billion stars in the background. The sun, we're not taking a picture of the sun. We're ignoring the sun. It's too bright for this camera. It's over here. And you can see it's changing in size because we're watching the passage by the sun where this thing dives down through the sun's atmosphere and goes away. You can see the Milky Way going by there. But you notice what it's seeing is all of these complicated outflows that I was showing you in the previous movie, taken from far away, now close up. And what you will see when this movie replays in a second is it's actually going to fly through one of these huge solar eruptions. And you won't miss it. It's really dramatic. And you can even see the moment when it passes through because all of a sudden the stuff sort of, parts like a curtain. Let's let it play again. It'll get there, I promise. Getting a little closer to the sun. You can see things, as we get closer to the sun, they get more dramatic and more energetic. And there's the eruption. And all of this outflow, and then in a second, the spacecraft's going to pass through that, and the view's going to kind of clear. And there it is. And we've actually flown through that. And in addition to taking these pictures, we can make measurements. We can stick a thermometer out the window and measure the temperature. It's not a thermometer, but you get the idea. We can measure the flow speeds. We can measure the magnetic fields. And we're actually sampling the sun's atmosphere, which we've measured out here at Earth for a long time, but now we're measuring at the sun and proving all of our theories right and many of them wrong. And we've also discovered that the sun is really dusty. All of these bright streaks that you see going by are actually dust particles that are getting blasted out along with the solar wind. And so that's one of the many discoveries. So this is the very most cutting edge, actually touching the sun and giving us the complete picture that we now have measurements in situ, measurements of literally sticking the thermometer out. We have remote sensing. We brought it all together. So, okay, I think I'm running out of time, so let me just wrap up. I hope today that I have conveyed to you that the sun is really cool, that we have a lot of ways to study it, that we are in a continuous system, that the stuff that's happening here that I've been showing you is actually touching us here on Earth in a real way. And so if you take nothing away from this other than the beauty of the sun, here are 3 lessons that you can draw, okay? The sun is dynamic. Its magnetic field stores and releases vast amounts of energy, these huge solar flares that we talked about. The sun's activity is driving space weather near Earth that actually matters to us and affects us on a daily basis, particularly now that we're at a period of solar activity. And space weather has, these impacts on our technological systems, but also unexpected ones, right? On agriculture, on animals. And we are literally living in the atmosphere of a star. Thank you.
So much, Dan. This is on. Are there questions? We have about 8 minutes for questions.
When you say dust particles, are you referring to the dust particles that you find in your home, or?
Yeah, it turns out that the whole solar system and actually all of interstellar space is filled with dust. And it's not always the same dust that you find in your home, but actually some of the dust that you find in your home falls in from outer space. So yeah, it turns out that the outer space is not really empty, and it's very, very, very dirty. There's just dust that's left over from the formation of the solar system and dust that's left over from comets getting evaporated by the sun, and it's everywhere. And it's a big challenge for people who build stuff that goes into deep space because it makes them dirty and it makes things not work right.
Thank you.
Yeah.
Other questions?
I'm Grant Gall, student here. Had a question. Can we predict the magnetic ejections? And if not yet, when can we, or do you predict?
Yeah, I didn't really talk about that. That's a whole challenge in of itself. And if you come to the workshop I'm going to do this afternoon, we'll talk a little more in detail about how that works. But the short answer is no. You know, we're really, even though people feel frustrated often with weather forecasts, we're actually pretty good at it on Earth. We have like measurements everywhere, right? You can put a wind sensor, a thermometer anywhere, and we have a whole fleet of satellites. And so we're really sampling the atmosphere, and we understand the atmosphere of the Earth pretty well. And so they can run these complicated computer models that more or less tell you what like tomorrow or the next day is going to be like. So on the sun, we have this limited set of observations I showed you. And then we have nothing, right? We see the sun, and then we make almost no measurements as things pass through the solar system, and then we have a couple of sort of last measurements of stuff right before it reaches the Earth. And it's a little like if you had to forecast hurricanes by like taking one picture of the atmosphere off the coast of Africa, and then you wait until the hurricane arrives in Cuba, and then you're like, oh, we're in trouble. And we really do not have the right measurements to fully capture the energy that's stored in the sun's atmosphere right now. We can get these beautiful pictures, but we can't make quantitative measurements of the magnetic field of the sun in the corona where all of these things are born. And so the way they do the forecasting right now is just to look at how complicated things are and use their gut. I'm not joking. That is the best forecast we have are people who've looked at a lot of stuff on the sun and can say, that thing looks dangerous, that thing doesn't look so dangerous. And we can do a little bit of that with some models, but yeah, we do not have the ability to forecast that. And so we're always reacting in space weather. It's one of the reasons that it's important for people to be aware of this, because we have very little lead time to prepare people. And so people who are in technological industries, power companies, satellites, they really have to be extremely flexible and reactive because things happen, and some of the effects travel at relativistic speed. They travel to the Earth in a matter of minutes, and boom. So no, the long answer is no, we can't do it, and it's something that we need to keep working on.
Other questions?
So as we saw, there's so many different kinds of activities happening on the sun. So is there any way humans can utilize all of that energy that's produced besides using solar panels?
Yeah, that's a really good question. I think today, definitely not. Is there a way you could use some of that energy someday? Yeah, maybe. I mean, the energy of these things sweeping over the Earth is enough to generate huge electrical currents in our power lines, and actually it can, any long piece of metal will be affected by this. So like railroads, currents will flow in the rails of the railroad, and they'll actually heat up and warp. So yeah, maybe there's some distant future where you could have a network of like long wires that could capture some of this energy, but it's not very efficient, and it's not very predictable or regular. So I think it's probably not where I would invest, but it's a really interesting idea, because you can imagine, right? I mean, these things are so energetic. If you could capture that, you could make all the energy we ever produced. But at the present, the sun is just too big, and we're not enough of a spacefaring race to interact with these huge structures in the way that would be necessary to really capture their energy. But yeah, it's a terrific question.
Excellent. Another question?
So the reason that we have life on Earth is because we're in like perfect distance from the sun, and we have tectonic plates and water cycle. With your experience, do you believe there's other planets like this with life on Earth like this, like multicellular?
Yeah, that's a really interesting question. I think We know there are many, many planets, okay? We have a whole bunch of space missions and ground-based telescopes that can detect planets directly and indirectly. You can see them actually cause little eclipses with their star. You can measure the wobble that they cause in the star. So we know there are, like, basically every star has planets. We have not seen a lot of planets that are like Earth, but that's partly just because of the sensitivity of our equipment. So that leads to the question, if there's all these planets, and there's probably planets like Earth, some of them surely are the right distance from their star to have life, why don't we ever hear from life anywhere else in the solar system? And that's a whole philosophical question that I don't have time to wade into, but I think it'd be really unlikely in a galaxy with, hundreds of billions of stars that there's not life on any of them. But it's a real dilemma that if life is common, we don't ever detect any signals from any sort of technological society out there in space. I mean, Earth is like leaking signals left and right out into space, and anybody within the galaxy with a good radio telescope would immediately know we're here, which some people think is very dangerous. But again, a discussion for another time. So yeah, I think yes, but where is it, right? That's the question.
Maybe one more, if anybody has one more question. We'll have to make it quick, though.
Are we actually going back to the moon in a few years?
Yeah, there's a whole program called Artemis that's going to send astronauts back to the moon. The rockets are ready, they're just testing them. The astronauts are selected, and it's kind of a matter of just getting all the technical pieces ready to do. It's in my field, it's a big deal because we need to be ready to make sure these astronauts actually survive the trip and don't get radiation sickness from their exposure to stuff like I was showing you. But yeah, it's going to happen. I don't know the exact timeline. It's not what I'm working on directly, but it's really going to happen. You're going to see men and women on the moon soon, within the decade.
Thank you so much, Dr. Seaton. We really appreciate it.
Yeah, thank you all.
All right, so we're going to have the next session with Lewis Ward here, and then also the CSC lecture hall will have the next executive session.